So another great cross-layer approach to improving energy efficiency is specialization. And this is a particularly hot topic in the research community right now. So the idea here is if I really want to decode a DVD and get the best performance at the least energy, the way to do that is to create a specialized piece of hardware whose whole job is just to decode DVDs. And then I can get much better energy efficiency, much better performance than I could running a software DVD decoder on a processor. And of course, the problem is that's specialized for MPEG-2. We're using H.264 now. We have a new video standard, and that awesome accelerator, which is so energy efficient and high performance, can do nothing to help me with these new video standards. So this tension between flexibility and specialization, I personally think is one of the grand challenges in the field. In the sense of how do we navigate this tension between general, less efficient architectures and specialized, more efficient architectures. And it's one thing that I'm looking at my research, but definitely across the community, many people are tackling this from a variety of different ways.
Now, if you have specialization, that implies that you have enough room on a chip
yes.
to put in all of these specialized functions that, at any given time, most of them are not being used.
That's right.
They're just being kind of wasted.
That's right. And so specialization makes less sense if area is a very, very tight constraint, because then I want to use every single transistor for as many purposes as possible. But we're kind of in this interesting domain right now where the number of transistors we can put on a chip far exceeds how many transistors we can actively use at any given time. So we need to think about creative ways to use those transistors. And so like you said, one idea is to use specialization. Yes, I've got a piece of my chip which I only use 10% of the time. But I couldn't really put anything else there anyways, because I don't have enough power to be able to keep it operating. And so there's this, this term in the community called dark silicon. The idea that if I look at a chip right now, a large portion of the chip is essentially dark, is not being used at any given time. And that it fundamentally changes the way you build systems. All of a sudden now specialization becomes more attractive. It doesn't need to be quite as flexible as it used to be. But can it be so specialized I can only use it, once every couple days? It can be that? No, it needs to be somewhat flexible. And so kind of navigating that tension is one of the really interesting research questions going on right now.
Now, we already have specialization on a system on chip of the smartphone, right? Because we have a video processor, an audio processor, and we have the general purpose apps processor. And in a very good example of specialization is a graphics processing unit, or GPU.
That's right.
And that's one of the reasons we get such eye-popping graphics out of our smartphones. So we talk a lot in the course about the organization of it's called the apps processor, the general purpose processor. So how is a GPU different in terms of its organization and how it exploits parallelism?
Sure.
Does it use instruction level parallelism, thread level parallelism, data level parallelism? So how does it work?
So I think in the course you've been talking about multi-core as well, right? So having multiple cores.
That's right.
So let's imagine we want to build a house, and let's say we have a bunch of carpenters. There's a couple different ways we could organize those carpenters. So multi-core processor is essentially the idea that we get our four contractors together, our builders together at the beginning of the day, and we say and they kind of collaborate together, and they say, oh, I'm going to work a little bit on the roof, I'm going to work a little bit on the floor, you're going to work a little bit on the walls, you're going to do the bathroom. And then they go off and they work on their piece of the house, and at the end of the day, they come back together and see how they did. So that's one way to exploit parallelism. And so this is very much kind of coarse-grained parallelism where each carpenter is doing a very different job.
You can think of each of those jobs as a thread.
Exactly. So each of those jobs is a thread, and they're doing kind of different things on different parts of the house at the same time. So GPUs exploit a fundamentally different type of parallelism called data parallelism. And the analogy would be, let's say I have a foreman who shows up along with my 4 carpenters. And the foreman's job is to organize these 4 carpenters. And the foreman says, you know what, we're not going to do 4 different things. We're just going to focus on the walls. I want all 4 of you to do the same thing on each of the 4 walls together. And so the foreman orchestrates the carpenters to essentially do similar tasks on different part of the house at the same time. Once they finish the walls, then they'll move on to the roof. Then they'll move on to the floor. One of the benefits of exploiting data parallelism is I could add another 4 carpenters, and they would just slip right in lockstep, do what the foreman says, and I could potentially complete the house much faster. Whereas if I have 4 carpenters that are all kind of doing their own thing, and I give it 4 more carpenters, and they have to kind of organize and synchronize and communicate, it's not clear that that's actually going to add that much benefit. So the key to graphics processors is that they exploit data level processing in the sense of they have a control processor, which is in charge of a lot of engines, which all operate in lockstep. Now, the idea of exploiting data parallelism with acceleration is a very old idea. And some of the original supercomputers were based on this idea. It's called vector processing. But vector processing had trouble making its way into the mainstream because of the stack, because it had a different hardware-software interface, which was challenging for compilers and programmers and applications to take advantage of. It required a PhD to make the best use of these high-performance vector processors. Essentially, what I think, personally, one of the key innovations of GPUs is that they have hidden that complexity, and they expose a different abstraction to software, which is easier to manipulate and use, namely the notion of many parallel threads. And if you can write code where you have all those threads doing different things, it just won't execute very efficiently. To get the best performance out of a GPU, you really want to orchestrate those threads so they're working on doing similar operations. And the GPU, the microarchitecture, takes care of dynamically aggregating those threads and those workers and getting them going in lockstep to get really great performance and efficiency. So I think that's one thing that makes GPUs different from CPUs. Now, there are many things that GPUs are good at that CPUs are not good at, or apps processors are not good at. But there's also many things that apps processors are good at that a graphics processor would not be good at, which is why modern smartphone and system-on-chip embedded systems have both. And this creates heterogeneity. Now, for a long time, I actually was I was very much a proponent of homogeneity, because if I have a homogeneous substrate, it makes it much easier to reason about, both in terms of the hardware and the software. But it's becoming increasingly clear that we're not going to have a homogeneous future. It's going to be heterogeneous. And on one hand, this creates tremendous challenges, but I also think it creates tremendous opportunities. And with challenges comes opportunities for students that are studying in this field in terms of how we manage this heterogeneity, whether it be in terms of software, whether it be in terms of hardware, or whether it be in terms of the new hardware-software abstractions to essentially manage this heterogeneity.